Okay, so it's time for our long-awaited discussion about what is entropy and an attempted reconciliation of all the various statements that are made about this quantity. So what we've got so far is that entropy is a state variable, and we've got the thermodynamic definition of entropy, which is that it's related to the amount of energy required to make a reversible and quasi-static change in units of joules per Kelvin. So it's not an energy in joules, instead it's a scaled energy in joules per Kelvin. And in some way, it reflects whether a process is reversible, reversibility, um, because the overall entropy change for a reversible process is zero. An irreversible process has an entropy change that's greater than zero. To proceed, an important set of definitions. The macro state of the system. That's the state of the system as defined by large-scale quantities like pressure, volume, and temperature, things that we can observe. The microstate of the system is um, the underlying state of all of the molecules, where they are, how fast they're going, and at what rate they're accelerating. For every single molecule. So if you had a mole, that would be 6.02 times 10 to the 23rd positions, velocities, and accelerations. Once you specify those, you specify the microstate of the system. Now, with those definitions, we're going to make a number of statements about entropy. We'll start with key fact number 2. There's a reason that this is 2, you'll see later. So first statement, there's many microstates that correspond to a given macrostate. Let's illustrate that with a familiar coin toss experiment. We'll flip a coin 4 times. So here are the results of the first flip. And it could be heads or it could be tails. Now, on the second flip, if you threw heads the first time, you could throw heads or tails the second time. Similarly, for tails on the first throw, it could be tail head or tail tail. On the third flip, these are all your possible outcomes. And then on the fourth, there's quite a long list. There's 2 to the 4 possible outcomes, 2 to the 4 equally likely microstates. These things here are all the microstates. So I didn't draw them all in here. There's a couple we still need to add. So tail, tail, head could be tail, tail, head, tail. Tail, tail, tail could be tail, 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 head, or tail, 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 tail. Okay, so these are all the microstates. Now, some of those microstates both correspond to the same quote-unquote macrostate. Look at these two. 2 heads and 2 tails. Okay? It's the same outcome. And we say that these are degenerate in that they are just different rearrangements of the same thing. Now, this applies to molecules because if you can think of head as one state of the molecule and tail as another state, if these were 4 different molecules, then you get exactly the same macro state if you just switch the states for the third and fourth molecule. Like this is the same pressure, temperature, and volume. So the macro states are just the things that you can observe. It's 4 heads, 0 tails, 3 heads, 1 tail, etc., etc., etc. And these each have different degeneracies, different repetition numbers, different, as we're going to say, multiplicity. Okay. Now, to measure the multiplicity, we're going to introduce the combinatoric coefficient. Oh, I should just go back and state what the multiplicity was, or the degeneracy. So these 2 words, we're going to use them equivalently. Degeneracy or multiplicity is just, and we'll define it later, the number of microstates, the number of degenerate microstates for a given macrostate. So this only happens one way. This happens, 4 ways. This happens 6 ways. This happens 4 ways. And there's only one occurrence of 4 tails. That's right out here. So if you go through the list and count them, this is the degeneracy of these macrostates. There are 6 microstates. There's 6 ways of having this outcome. Now, another way to express that is using combinatorics. Combinatorics n choose k is defined using factorials. N factorial means start at n and multiply by 1 less and then by 2 less all the way down to 1. 0 factorial is just defined as 1. So 4 factorial is 4 times 3 times 2 times 1. Now, in terms of factorials, n choose k is n factorial over n minus k factorial times k factorial. Now, this comes up in binomial probability, like coin tosses, because if you throw the coin n times and you want k heads, that's n tosses choose k heads. It's n choose k. Let's show that that works. Here was the macrostates for our coin toss experiment. If you want 4 heads and 0 tails, so that's 4 tosses, choose 4 heads. By definition, that would be 4 factorial over 4 minus 4 factorial times 4 factorial. Now, 4 minus 4 factorial, that's 0 factorial. That's just 1, so this is just equal to 1, so it's consistent with that. For 4 tosses, choose 3 heads. Let's show that it works out to this number here. By definition of n choose k, it's 4 factorial over 4 minus 3, which is 1 factorial, times 3 factorial. So we have to expand there. 4 factorial is 4, 3, 2, 1. 3 factorial is 3, 2, 1. And this bracket here, 4 minus 3, it's pretty messy, sorry. Let's try that again. 4 minus 3 factorial is just 1 factorial, which is 1. But let's try and write neatly here. There we go, that's better. So that's 4. All right, so again, consistent. Let's try this one. That's 4 tosses, choose 2 heads. Definition is 4 factorial over the difference factorial over the k factorial. So this is 4 factorial over 2 factorial, 2 factorial. So there's the first 2 factorial. There's the second one. 2 times 2 is 4, and it cancels out, so 3, 2, 1, it's 6. Yes, indeed, it works. Okay, so key fact 2 said that there's lots of microstates for each macrostate. Key fact 3, the most likely state based on the laws of probability is the one with the highest degeneracy or multiplicity. Well, for probability theory, we know that the probability of something happening is the number of desired outcomes over the total possible number of outcomes. So for our coin toss experiment, there were 2 to the 4, which is 16, possible outcomes for our 4 coin tosses. And if we look at our macro states, for the 4-head macro state, there is only one possible way to get that. So the probability of that happening is 1 in 16. On the other hand, the 2-head, 2-tail outcome had 6 ways that that could happen out of 16. So this is the most likely. So the most likely state, just based on the laws of probability, is the one with the highest multiplicity. Now we're going to introduce a symbol, omega. And omega is going to stand for the number of degenerate states, the degeneracy or the multiplicity of the macrostate. So what this key fact above tells us is that the outcome with the highest omega, that's the one that's most likely to occur just based on the laws of probability. Now, if we start to imagine a thermodynamical example, then instead of coin tosses, let's look at a gas in a box, and let's say it's a box with 2 sides, and we at one point have all the gas on one side, so we pump out this side, so it's a vacuum, and then we open up the partition so that the gas can spread around the box. Now, a little bit later, it is entirely possible at first glance that, you could, if you waited long enough, get a state where all the molecules would be on this side. But there's only, for n molecules, n choose n ways that that could happen. There's only one way that that could happen. On the other hand, there's lots of ways that you could end up with the molecules evenly distributed. So for n molecules, you could choose n over 2 on the right. Now, it turns out this is a pretty big number, especially if n is a mole. Now, if we're just doing left and right, this is, again, binomial probability. There's, again, just 2 to the n outcomes for this experiment. So the probability of all the gas molecules ending up over on this side is just 1 over 2 to the n. The probability in this case is this ratio. Now, we'd have to work this out and use something called Stirling's approximation, but we're going to see that there's a significant probability that the molecules will be divided evenly between both. And so the probability here is just 1 over 2 to the n. And if n is anything significant at all, I mean, if n is 4, then I guess 1/16th chance that 4 molecules could end up on this side of the box. But if n is a mole, then this probability basically tends to 0 for any significant number of n. So that it's not really ruled out, like it's not impossible to happen, but practically the probability is so small that you'd have to wait longer than the lifetime of the universe for it to have any chance of occurring. Okay, so it's now time for our first key fact. And the key fact is that entropy is proportional to degeneracy of the macro state. Now, why is this? Well, let's consider what happens when a little bit of thermal energy flows into the system with no work. Well, the internal energy is going to go up as a result of that extra energy. The entropy of the system is going to increase. And then one of three things will happen, depending on what sort of process you're looking at. I mean, either the temperature will go up, or a little bit more mass will change phase, dq over the latent heat, or the last thing that can happen if a little bit of thermal energy flows in, if you actually are doing an isothermal process, then the temperature won't go up, but what will happen is the volume will increase a little bit, and we could show that dV is V over nRT times dQ. That comes from the fact that dW is the opposite of dQ for an isothermal process, and the little bit of work is minus pdV, which is minus nRT dEV over V. So minus dQ is this, then you just cross multiply and you get this relationship here. So the point is, though, that when a little bit of dQ flows in, the macro state of the system is going to change because there's more internal energy. There's either more temperature or more volume. So that's a different macro state as a result of that thermal energy transfer. At the same time, however, not only is the macro state changing, but the number of microstates is changing. The reason for that is that, and we draw these sorts of graphs in chemistry, when at a certain temperature, high energy microstates are not going to be populated because there's a factor called the Boltzmann factor, which is the exponential of negative the energy of the microstate over k times t. And if the energy is really big, then this is a big number, and e to a minus big number is basically 0. So as this curve shows, when the temperature is cold, there's really no chance that these microstates, these high energy microstates, will be occupied. However, as the temperature gets bigger, represented here by a big T, now this ratio isn't so big anymore. In fact, it could get quite small, and e to a negative small number is appreciable. And so as we see here on the curve, now these higher energy microstates are occupied at higher temperature. So when a little bit of thermal energy flows in, let's say we're dealing with that first case, the most common sort of reasonable case where the temperature goes up. If the temperature goes up, then these higher energy microstates get occupied and the multiplicity goes up. So here, there's now larger, yes, the multiplicity has now increased. So when dQ flows in, omega increases the multiplicity. But we know that when dQ flows in, that S increases, the entropy increases as well. So that just really reinforces the fact that they're in direct proportion. So to make this argument quantitative, you need something known as the Boltzmann factor. And this is a postulate that Boltzmann made about the population of a quantum state, or the probability that a system can be found in that state. And here's his factor. E to the minus energy over k times the Kelvin temperature. We have to divide by a normalization constant because the total probability has to be 1, and this is called z. And it's actually a really important quantity. It's also known as the partition function, and we'll talk about that a little bit more when we reach our introduction to statistical mechanics. So because of this, as we've said, a higher temperature leads to an increase in probability for the high energy states, i.e. an increase in multiplicity. So when a little bit of thermal energy comes in, the entropy goes up, the macrostate changes, but so does the number of microstates, so does the degeneracy. So it makes sense to say that entropy is proportional to degeneracy, omega. Now, since entropy is proportional to multiplicity, here's a little proportionality symbol for you, and we know already that the most likely state is the state of maximum multiplicity, it follows that the most likely state of a system is the state of highest entropy. So we hear in chemistry all the time that there's a tendency towards maximum entropy. And that really just means it's just referring to the laws of probability, because if all microstates are equally likely, when you have the most degenerate microstates, that's the most likely state, and the most degeneracy correlates to the most entropy. So there's our fourth key fact. The most likely state of a system is the state of highest entropy. Some more facts. We've heard that already in the course that entropy of the universe never decreases. Let's just pretend we have two objects, and let's just look at the case of just a little bit of energy transfer, dq, between them. Now, this object here has lost thermal energy, so its multiplicity, its entropy is going to decrease. And we can state that ds is negative dq over t1, let's call it. Let's say this one's at t1. And we're going to pretend that these objects are large enough and that little bit of thermal energy is small enough that the temperatures basically remain the same. So we've got thermal energy flow into the second object, so its entropy is going to go up. Entropy change object 1, entropy change object 2. It's the same amount of dq, but it's at a different temperature. So if we find the total ds, it's just, ooh, that's messy. The total entropy change in this process, total ds, it's just the sum of these two. So it's minus dq over t1 plus dq over t2. Dq is the same, so it's 1 over t2 minus 1 over t1. Now, because thermal energy will only transfer spontaneously from a hotter to a colder object, T1 has got to be greater than T2. And if T1 is greater, that means its reciprocal is smaller. That means this is going to be greater than 0. It's going to exceed 0. Now, the only way that it could possibly, the smallest it could possibly be, is equal 0. And that's going to happen when T1 is really, really, really close to T2, okay? And they're equal to each other, then the entropy change will be 0. And that's really what you have to do to have a reversible change. You have to have a really tiny, tiny temperature difference between these two reservoirs. And just a little bit of thermal energy will then flow between them, just an infinitesimal difference. Okay, so the entropy of the universe never decreases. Delta S is going to be greater than 0 for most processes and equal to 0 is the best you can get, and that's for reversible and quasi-static processes. Multiplicity and entropy tend to increase in all cases, other than reversible and quasi-static processes. Okay, now, compounds have a characteristic entropy. It's the entropy that is needed to make them. And we can find that just by starting at absolute 0 and then just adding up. So ds will be add up dq over t. And this will be the entropy. It's actually the delta S for that material. Now, what do we integrate? Well, when we are getting a changing temperature, then dq is ncp dt. Okay, so that's when a little bit of energy creates a temperature change. But of course, at phase changes, a little bit of thermal energy doesn't make a temperature change. Instead, dq is L times dm. So that's the dq when you're undergoing a phase change. And so you basically integrate, there's a phase change, there you integrate over changing temperature, there's a phase change, and so on, and you add all those things up, and these are the little changes in entropy all the way up, and then you end up, in this case, with nitrogen gas at 25 degrees, having a standard entropy of 192 joules per Kelvin. So because it takes energy to make a substance, it also takes entropy to make the substance, and therefore materials have characteristic entropies. Now, these characteristic entropies vary from one material to the other for the same reason that specific heat capacities vary from one material to the other. So if you are heating up an object, then you're adding thermal energy in. And if no work is being done, then the internal energy change would be the same if you're warming up two materials and you're adding the same amount of dq. However, the temperature change will be different. And this is, of course, because, dq is ncp dt. So with a different specific heat and the same dq, you get a different temperature change. So here in this first material, let's see, we add dq and we get a temperature change dt. Here in this second material, we might get a much smaller temperature change for that same amount dq. So that to get this one to the same temperature that this one was, we need more. We need more, that says more, believe it or not, q to get the same dt that we had here. Okay, so we just changed the font size there so it looks a little better now. So yes, with this dq, you get a temperature change, big dt. With the same dq, this material doesn't change as much because this material, we can see, must have a large constant pressure specific heat, and this first material has a smaller constant pressure specific heat. So on the macro scale, we can say that this is happening simply because they have different specific heats. And therefore, with the same dq, you're not getting the same dt. And therefore, because you don't reach the same temperature, this ratio starts to change, and the entropies for the two materials are different. On the micro scale, what's really happening is these materials have different energy levels, and therefore dq for one material gives a different change in the available microstates than dq would for another material. So they get different multiplicity changes. Or see later in the course that the constant pressure specific heat is related to how much entropy changes with temperature at constant pressure. So entropy changes in materials are related to the specific heat capacity. And we can see numerically here in a chart, the standard entropy of formation gets bigger when you have a bigger specific heat. So there's a correlation between the two, entropy and specific heat. Here, oxygen was a little bit less in terms of its entropy of formation. It's also a little bit less in terms of its specific heat capacity. So our key facts say that entropy is related to multiplicity, that it varies, that materials have an intrinsic entropy, that it varies between materials for the same reason that specific heat varies, that entropy is a maximum for the most likely state because of the laws of probability. A final thing that's often, a couple of final things about entropy. It is often said that it represents energy that is unavailable. You see, because there's an energy cost to multiplicity, then any process that was, say, releasing energy but increasing multiplicity will find that the available energy, which we call the free energy, isn't just the same as the energy released. Because if there's a change in entropy, some energy must inevitably be used to build up the entropy of the final state. And so what you get out of it, say if S goes up in a certain process, say like burning gasoline, then this takes energy. Right? Thermal energy will be needed to build the new final state. And so that thermal energy reduces the amount of energy that's available as a result of this process. There's less energy available. And this is why we define the free energy parameter. So entropy, in a sense, is the joules per Kelvin that's locked up, unavailable, due to multiplicity, as I sometimes call it. It's the energy cost of multiplicity. And when you're building something, you have to pay that energy cost. The final thing that's often said about entropy is that it reflects disorder. Now let's think about that. If we were to look at, say, our coin toss experiment or our gas experiment from earlier, we would say that an ordered state, if you look at it, clearly has very low multiplicity. And therefore, we know it's also got very low entropy. A disordered state, you can see here, there's lots of ways of making this disordered state that has a relatively high multiplicity, and therefore a very high entropy. So it is intrinsically true that more entropy corresponds with more disorder, and that there is a probabilistic tendency towards, or what we call a driving force, towards greater disorder. But the tendency is really just towards greater multiplicity by the law of probability. There isn't anything actually pushing the system to go that way. It just, as the system passes through macro states as it goes to equilibrium, the most likely macro state is the one with the greatest underlying multiplicity. So it's really just the laws of probability that are driving this process. So I don't use this formulation. I don't say it reflects disorder because it can lead to some confusion. And ultimately, the way to connect all of these disparate facts about entropy is through the concept of multiplicity. So entropy, which we define thermodynamically as a little bit of dq over t for reversible and quasi-static processes, is related to the multiplicity or degeneracy and we use the symbol omega of the macro state. It varies between objects as reflected in the specific heat capacity, and it increases as we add heat, because as you add thermal energy, the degeneracy will increase because you can reach more microstates, and therefore omega goes up. So, to connect and understand all of these disparate observations about entropy, the key is to connect our thermodynamic definition of entropy with the statistical definition of entropy, which says that it's proportional to the degeneracy. Later in the course, we'll actually define it as the natural logarithm of the degeneracy. But more on that later.